Welcome back. So in this video we're going to be looking at atomic structure. We'll do a quick introduction to how the atomic model has developed over time, and then we'll move into practicing a bit more about our atomic structure and expanding on what we have already done in junior science and year 10. So let's get going. We don't need to know the history of the atomic model in terms of the scientists and the dates, but you really should have an understanding of how the model has changed over time and continues to alter. This is particularly relevant when we're talking at things like TOC, where we look at the use of models to show ideas that we can't necessarily visualize directly ourselves, and how scientific information changes over time, building on these models and changing them, that they're never really fixed, that they change with changing evidence and changing understanding. So as new knowledge comes about, we need to adjust the previous paradigm, I guess, to account for that. The atomic model is no different. Our first recorded writings of the atomic model start with Aristotle and the ancient Greeks, and the idea that matter was continuous, that there was an ether and then it just went on and on and on. It was in the 19th century that Dalton came up with the idea of atoms, and then later on in that century, Thomson came up with what we call the plum pudding model, which is this one here, which looks at strong areas of charge surrounded by sort of another sort of medium of charge, sort of like raisins in a plum pudding or things like that. After that we get Rutherford, which is one that you may be familiar with because it's one that we often see being shown as, I guess, it's what we call the nuclear atom, and you'll recognize this perhaps as like the Big Bang Theory logo and things like that. What this is showing, Rutherford actually discovered the nucleus. Prior to Rutherford, we didn't know that the nucleus existed, and he discovered that nucleus is a hard, positive, dense center surrounded by orbiting electrons. In this one, in Rutherford's model, all the electrons orbited like the planets around the sun, and what we've discovered that this is not necessarily the case. In Rutherford's model, they all had similar energies, so the orbits would all be equidistant from the center, but it wasn't until the beginning of the 20th century with Bohr, Niels Bohr, that the evidence showed that this was not the case. So this is the model that you're probably most familiar with in your studies up until now. The idea that electrons inhabit shells, that these shells have different energy levels, and that we fill them from the inside out, and that a valence shell is full when it has 8 electrons. So this is known as the Bohr model. After that, in the 1920s and 30s, we had the discovery of nuclear physics and the quantum mechanics model. Schrödinger and Chadwick then discovered the neutron. After Chadwick discovered the neutron, it really opened up our understanding of atomic mass and things like that. So in these models, we still have the electron being a dense central positive core, the nucleus full of protons, but now our electrons don't orbit in set shells or rings. What they are is, I guess the easiest way to describe it is a region of mathematical probability. And we'll talk about that a little bit more as we go on in class and develop these ideas. But this is where we're at now, and our idea of the atomic model stays pretty fixed at this point so far. Physicists have come across subatomic particles, which have changed the nature of particle physics. However, it hasn't really changed the way we look at the model of the atom in terms of how it behaves in chemical reactions and things like that. So this is a quick summary of those key scientists that were crucial to the development of this model, and as you can see, it is from the contributions of numerous people that this model has been built up, particularly in terms of the modern quantum cloud model, since we have the discovery of nuclear physics, which really opened up our understanding of these areas. So for us, what we're really looking at in terms of modern day specifics is what we understand an atom to be, is that all matter is made of atoms, that atoms are neutral So they're uncharged. So an atom of chlorine is uncharged, an atom of hydrogen is uncharged. Pretty much, if we can read it on the periodic table as it's written, it is uncharged. So it's neutral. It will have an equal number of electrons to protons and not carry either a positive or negative charge. They consist of electrons, protons, and neutrons. The protons will determine the nature of the element. The electrons will equal a proton in a neutral atom. And then we have, while we consider these the three basic particles, there's over 50 subatomic particles now in the subatomic family, which if you're studying physics, you'll learn a lot more about, but we don't tend to work on in chemistry. So the main ones we're interested in is still looking at, largely we're still going to talk about our model being protons and neutrons in the nucleus, and we refer to these as nucleons because they are contained within the nucleus, and then electrons surrounding this nucleus in an electron cloud of differing energy levels. So when we look at this, we need to have an understanding of the relative sizes and position of these. So if we look at our protons, neutrons, and electrons, we can see if we try and write their mass in kilograms, we end up with a very, very large exponent, so 10 to the negative 27, which means they're very, very, very small when we're talking about trying to figure out relative size in terms of kilograms. It's just not feasible for us to picture a size this small or a mass this small. Again, they also have individually quite a small charge, but the charge is actually a bit larger compared to their relative mass, I guess. So rather than talking about their actual mass in kilograms and their actual charge in terms of how much electricity they would carry and things like that, we give them a relative mass and relative charge to each other. In this case, the relative mass of the proton and the neutron, you can see here 1.6726 times 10 to the negative 27 versus 1.6749. Relatively, these are the same number when we're talking about something that small. So they have a relative mass of 1 each. And then we can see here that the electron's actually much smaller than this, 5 times 10 to the negative 4. It's actually about 1/2000th the mass of a proton and a neutron. So when we say that the mass of an atom is made up from the protons and the neutrons, that's because the electrons are so small they don't really contribute anything to that overall mass. Adding in even 100 of them makes no difference to the overall mass of the atom. The relative charge, however, you can see here that the neutron has no charge, 1.6022 times 10 to the negative 19. It's actually much the same in magnitude, but the electron is opposite in size. So they have a relative charge of +1 and -1, respectively. Both of these are found in the nucleus, so as I said, they are called nucleons. When we refer to nucleons, we're talking about the neutrons and protons, the subatomic particles that are in our nucleus, and then our electrons orbit the nucleus. So all atoms are neutral. Number of protons is equal to the number of electrons. Be sure that you get this the right way around. A lot of people assume that the protons equal the electrons, and it's actually the other way around. The electrons equal the protons because the protons are what set the element. If I change the number of protons, then I change what element it is I'm talking about. So that's actually the critical number that we're interested in. This number is known as the atomic number and is given the symbol Z, and then the number of protons plus neutrons is known as our mass number, A. Okay, so make sure you've got those in your notes because these are ones that you need to know the definition of and the symbol for. So atoms with the same number of protons but different number of neutrons are referred to as isotopes, and we will look at those a little bit more. So the atomic number, as I said, is the number of protons in the nucleus, and it determines the element. Anything with 1 proton is going to be hydrogen, and anything with 7 protons will be nitrogen, and always nitrogen. So the number of protons sets the element. So that means that the atomic number for an element will always be the same. Luckily for us, the atomic number is on the periodic table. So we can see here carbon has the atomic number 6, and that's printed on the periodic table. The one that comes after it, so one more proton, is 7 protons, and that is nitrogen. So if we look at the periodic table, we will always know how many protons something has, and then we use this symbology here where we replace X with the symbol from the element. Z is our atomic number, okay, so our number of protons, and then A is our mass number, which is our number of protons plus neutrons at this point in time. So this is our periodic table, and remember you will have a periodic table with you in all pieces of assessment and should have your data book with you at all times in class. So now that we know what the atomic number is and we've defined those, we can move on from that and learn how to write these symbols a little bit better. Let's have a little bit of practice filling in this table. So as we can see here on the left hand side, we have our protons, neutrons, electrons, and atom across the headings. So if we look here on the first one, we have 5 protons, 5 neutrons, and 5 electrons. So that will mean that the atom will be boron if we look that up on our periodic table. So what I'd like you to do is actually pause the video and complete this table by using your periodic table, and then come back and check your answers. Hopefully you were able to fill out the table, and you will know that the first atom was boron, calcium is 20 protons, beryllium was our next one, chlorine, fluorine is atomic number 9 and has 9 protons, sodium is atomic number 11 with 11 protons, and of course hydrogen is element number 1. So with this, as I said before, the neutron is one of the last things that was discovered. So Chadwick discovered the neutron in 1932, and what this meant was it allowed us to understand that atoms could have masses that varied depending on the number of neutrons that they had. Okay, so as I said before, the neutrons and protons in atoms are known as the nucleons, and the neutrons really help to reduce the repulsion between the positive charges in the nucleus. If you think we have a lot of positive charges grouped together, and therefore that means that they would normally repel each other. Okay, so the neutrons actually distribute that charge a bit better and make this nucleus more stable. With this, it meant that now we have atoms that when we look at the mass number, it's a combination of the protons and the neutrons, and if we differ the number of neutrons, we end up with what we call isotopes. So this meant we need ways to describe what the different forms of an element may be. So because the mass number is the number of the nucleons, protons and neutrons, we can determine the number of neutrons by subtracting the atomic number from the mass number. And then we can show that by having the symbol in the middle, as we said before, atomic number at the bottom left-hand side, and our mass number or nucleon number when it's a whole integer as the number on the top left-hand side. This means if atoms have different masses, we have a way of differentiating between the two of them. So this summarizes how we write our atomic symbol, and we call this nuclide symbol notation. Okay, so if we talk about a nuclide symbol or an atomic symbol, we're talking about the symbol that shows both its atomic number and its mass number. So here we go, a couple of questions that we'll go through quickly, and then we will wrap this video up. So have a go at writing these in your notes. So the definition of mass number, the definition of atomic number, and then the mass number and atomic number in each of the examples that you've used. So if we use these definitions, we can now look at these questions here, where we can determine the number of protons and neutrons in each. So here we have carbon, and with 6 on the bottom, so this is my atomic number, so this is 6, so it has 6 protons. And then the mass number which is equal to A as our symbol is equal to 12. So it has 12 mass number in total, so 12 nucleons. 6 are protons, so 12 minus 6 will give me 6 neutrons in this one here. Okay, and then we could assign those for each of these. Chlorine has 17 protons, so chlorine 37 will have 20 neutrons. Rubidium 44, 101, it's going to be 101 minus 44 is going to equal the number of neutrons. So make sure you finish these two and put them in your notes to have checked off.